right, well, we need to review some things that we talked about a week and a half ago. Now, that's not going to make any sense to you if you happen to be watching on YouTube, but they just had spring break, and they haven't thought about geometry or triangles or parallel lines or proportions or anything for a week and a half. They had strict instructions not to think about it at all, so I'm not going to ask if you did, because if you did, you're a sinner. But you should not have been thinking about it at all, which means I'm going to take the next few minutes and refresh your memory on some things. So you don't necessarily have anything out, just we're watching, and let's see what we can recall. It was a long time ago, back when you were very young, that like a week and a half ago, that I introduced to you this, actually it was more like 3 weeks ago that I introduced this picture to you, a triangle with a line drawn parallel to one side. And this little line here divided these two sides into two segments each. And we had 3 different proportions in words that went with this picture. I'm curious whose brain actually remembers one of them.
Bottom to top, bottom to top.
Hey, bottom is to top as bottom is to top. Good. Okay, Chris, you had your hand up.
Whole is to bottom, whole is to bottom.
Whole is to bottom as whole is to bottom. That's 2 out of 3. Does anyone remember the third one? Audrey, you do. Whole is to top as whole is to top. Hey, that's really good. All right, this is the great thing about having a third hour. First hour, y'all would have remembered squat.
No.
But you did remember something. Okay, that's good, that's good. Another picture that we had involved a triangle with a bisected interior angle. And when you bisect one angle, that bisector goes across and it hits the other side, and it divides the other side. Now, it doesn't bisect the other side necessarily, but it does divide it into a couple of segments. And we had a proportion that went with this picture. Anyone besides my 3 helpers already? Any of the rest of you remember this proportion? All right, Jamie?
Is it segment 1 is to segment 2 as side 1 is to side 2?
Well, there we go. Segment is to segment as side is to side. Say that with me, class. Segment is to segment as side is to side. Now, I know this is really brutal to do this to you after a week and a half off, but I'm going to do it anyway. We also have the same picture with an no, that would be brutal too. Hey, that's a great idea. Good job, Chris. Students are like, we're leaving. But if we were to, high school dropouts, all of them now. That was quick. All right. But we could also bisect an exterior angle. And that would still divide this side, but it would divide it externally out here. But it would still be in words, segment is to segment as side is to side. But remember, if this is side AB and this is point P, my 2 segments of AB are, anyone in letters?
B is to A.
BP and AP would be your segment. Just like if I put P right here, you'd say AP and BP, right? Well, it's not right there, it's out here, but it's still AP and BP. Let's call the triangle ABC, and it's going to be segment is to segment as side is to side. Do we remember learning that? Okay, coming back to us here. Most of you nodding. Genesis, are you awake?
No, barely.
Yeah, barely. All right. This is a tough transition back to school, I know. Let's see. We also had a picture with lots of little parallel lines and stuff. Pretend those are parallel. We don't trust our eyes, remember that? And we have a couple of transversals, for instance.
What are eyes?
We could call these segments Q, R, S, T, U, V. And there was a proportion, we're actually going to use letters here since words would be kind of challenging, but if you go with this picture, if indeed those were parallel, Quentin, do you remember the proportion?
QT is to RU.
Q is to T.
And R is to S is to.
There we go, right? This segment is to its matching segment, corresponding segment. This little segment is to its corresponding segment. This segment is to its corresponding segment. Of course, that pattern could be repeated. We had a similar idea with just 2 parallel lines and a whole bunch of transversals, as long as the transversals all came from the same point up here. So if I call these segments A, B, C, D, E, and G, then we could represent proportion based on these letters here. I at least got the smirk out of Audrey there. But Kendall, we're going to go to you and see if you remember how we could set up a proportion based on these letters.
A is to B, as B is to C, E.
That's an E.
As C is to G.
There we go, good. Now, of course, that's if I named these A, B, C, where A represents the entire segment. Of course, if I called these points A, B, C, and D, then we'd say AB is to D, as BC is to E, as CD is to G, and so forth. Okay, that's, I think, where Quentin seemed to be a little confused there. So capital letters, again, would be points. Lowercase letters can represent entire line segments. We had another picture more recently that had a right angle, therefore a right triangle, and an altitude drawn down from the vertex of the right angle. This was the most recent picture. In fact, everything that I've showed you already has been tested on your exam that you took just a few days before we went on break. This is the one that hasn't been tested or quizzed yet, actually. Just thought I'd throw that back out there. And so there is a proportion based on this picture, this right triangle with an altitude drawn from the vertex of the right angle down to the hypotenuse. And it's based on the fact that there are how many triangles in this picture, Genesis? 3. The whole triangle we started with, and then by drawing this altitude, I got 1, 2 more triangles, 3 triangles. And Genesis, it's important to remember that all 3 of those triangles are similar to each other. And we know, class, that if triangles are similar, their corresponding angles are equal, and the corresponding sides are proportional. So since there are 3 triangles, it makes sense there would be 3 proportions we could form. Does anyone remember one of the proportions in words? Chris?
Segment is to leg is leg to altitude, or leg is to hypotenuse?
Segment, and you could take either this segment or this segment. Segment is to its leg, or segment is to its leg, as that same leg, or segment is leg as this same leg is to the hypotenuse. So if we call this segment 1, this would have to be leg 1. If we call this segment 2, of course, then this would be called leg 2, and of course the hypotenuse is the hypotenuse. There's only one of those in the triangle, right? So we can say that segment is to leg as leg is to hypotenuse, or segment is to leg as leg is to hypotenuse. That's because each of these triangles is similar to the entire triangle. But because these 2 triangles are similar to each other, there's a proportion we could use with them. Do we remember in words the other proportion? Somebody besides Chris by any chance? If not, I'll go back to Chris. They're like, yes, we're off the hook. Okay, Chris.
Is it leg is to altitude, or is it segment is to altitude is to leg?
Somebody help him? Did that ring a bell for you, maybe? Quentin?
Segment is to hypotenuse, or segment is altitude, hypotenuse is segment.
No. It was segment is to altitude, as altitude is to the other segment.
Close.
Segment is to altitude. That's why when you said it, I was like, he's so close. I wonder if that triggered it for somebody else. Segment is to altitude as altitude is to the other segment. So let me give you some letters here, and let's see if we can, now that we've had that quick refresher. In fact, let's say those together. There's 2 of them in words. Let's start with the one we just did. Say it with me, class. Segment is to altitude as altitude is to segment. Again, segment is to altitude as altitude is to segment. And the other one, we're going to say twice because there's 2 ways it applies. Say it with me, class. Segment is to leg as leg is to hypotenuse. And segment is to leg as leg is to hypotenuse. So if I gave you letters M, N, O, P. 3 proportions in letters we can use. Only 2 in words, 3 in letters, because 2 of them kind of match. Can you give me one of them in letters, Genesis?
Is to M-O.
So segment is to leg as,
O-N.
or you could say M-O again is fine. Segment is to leg as leg is to
M-N.
hypotenuse, and then there we go. How about another one? Ethan, you've been quiet for a while. It's a nice change at first. Just kidding. You've been quiet the last week and a half. All right, go ahead.
MP is
Sorry, was that M or N?
MP
MP, okay.
is the OP.
There we go. So segment is to altitude as altitude is to the other segment. Good. Where the altitude is the mean proportional between the segments of the hypotenuse. Good. Or the leg is the mean proportional between its adjacent segment and the entire hypotenuse. One more in letters, and Jamie.
PN is to OP as OP is to PM. Right now we've already done that.
Right, that's essentially the same one. You just did an alternation, right? But it is technically true. Segment is altitude is to segment. I'm looking for the other sheet. Genesis gave me segment is to leg is to hypotenuse. I'm looking for the other version of that.
Is that PN is to NO as NO is to MN.
There we go. I was going to say no, but no, you're correct. There we go. Segment PN is to leg no, as leg no is to hypotenuse MN. Okay, so that's where we kind of left off. We're going to get a little bit of practice with that later on this hour. But I told you that this was the last theorem before the big one, the one that you first learned about before you even knew what a theorem was. That was the Pythagorean Theorem, and that's what we're going to prove now, but it's going to be based off this picture. So notebooks out, if you would turn to the Theorems Corollaries section. Theorems Corollaries section. And it's time to finally prove that your junior high math teacher was not lying to you when they told you that c squared equals a squared plus b squared. So I'm going to defend your junior high math teacher. I was not any of your junior high math teachers, so I'm not defending myself in this instance. But Theorem 62 says this: the square of the hypotenuse of any right triangle, that's important, any right triangle, this has to be true. The square of the hypotenuse of any right triangle equals the sum of the squares of the legs. Equals the sum of the squares of the legs. The square of the hypotenuse of any right triangle equals the sum of the squares of the legs. And then if you would, after you're done, in parentheses, write Pythagorean Theorem. But we just say it Pythagorean Theorem. All right, but it's spelled Pythagorean Theorem. The Pythagorean Theorem. The square of the hypotenuse of any right triangle is equal to the sum of the squares of the legs. Once you have that down, turn to the proofs of theorems corollary section. We're definitely proving this one, okay? We've had really several where we've talked through proofs and actually done them. Okay, we have to prove this one.
Be a really good one.
All right, and if you would, go ahead and at the top of a new sheet of paper in your proofs of theorems corollary section, go ahead and write Theorem 62, Pythagorean Theorem, at the top of the page. And then down below, draw a right triangle. We'll call the right angle C, as is customary, and we'll call the two acute angles A and B. Again, that's why the lettering usually works out that C, little c, is the side across from angle C, little a, the side across from angle A, and little b, the side across from angle B, which is why it said c squared equals a squared plus b squared. Okay? You don't actually have to label the small letters or the lowercase letters, but I did want to go ahead and show that. So Theorem 62, the Pythagorean Theorem. And we're going to be given right triangle ABC with right angle C. Right triangle ABC with right angle C. We are going to prove the c squared equals a squared plus b squared. But here's how we're going to write it. C, meaning the hypotenuse, is actually going to be called side AB. So AB squared equals a squared. Well, a is really side BC, so BC squared plus side B would be AC, so AC squared. AB squared equals BC squared plus AC squared. Using capital letters and 2 of them. It's going to be easier for the proof if we do it this way instead of the c squared equals a squared plus b squared. So given a right triangle, ABC with right angle C, so not told anything special about the right triangle. This is true of any right triangle, no matter what it looks like, as long as there's the right angle in it. We want to prove that the hypotenuse's square equals the sum of the squares of the 2 legs. Once you have that down 2 columns, statements, reasons. And you're like, yep, we're back in school now. It now feels real to me again.
Starts crying.
As soon as he says 2 columns, statements, reasons. Hopefully we weren't having proof nightmares during spring break. You were, Ethan?
I cried myself to sleep every night because of it.
You missed it so much, Chris?
Something like that.
All right, statements, reasons. Get down your first statement, your first reason. Got right triangle ABC with right angle C. Now I told you that this theorem closely followed the previous theorem. It's not corollary, it's not quite that close, but the previous theorem was what led to this. The big difference is the last theorem there was an altitude, and this doesn't have an altitude. So, Ethan, what do you suppose we should do?
I hate auxiliary lines.
Yeah, let's use an auxiliary line. Let's go ahead and draw the altitude, the perpendicular, right? So, to the best of your ability, try to get the line that would go straight across perpendicular. Well, let's call it CD. Again, it doesn't have to be perfect. We don't trust our eyes. But number 2, draw altitude CD to AB. Draw altitude CD, let's go to perpendicular to AB. Reason, it's not 2 points determine a straight line, right? Because we didn't know where point D was. Thoughts? Been a little while since we've done one of these. Not definition of perpendicular.
Definition of altitude.
Well, the fact that it is a perpendicular.
Definition of angle bisector?
It's definitely not an angle bisector. Here's the thought. From a point, C, how many perpendiculars can I draw?
1.
Only 1. So when I say to draw that perpendicular or that altitude, there's only one you can draw. And that's our reason, is that only one perpendicular may be drawn to a line from a point. So we're saying we're drawing the perpendicular. There's only one. Okay, there's not another one there. If there had been another one there, we couldn't have drawn this one. But there wasn't already one, so we could draw it. We've got our altitude CD perpendicular to AB. Now, as soon as we got that altitude drawn, that perpendicular drawn, then everything that we've stated previously about the altitude drawn to the hypotenuse is now valid, right? Segment is to leg is to hypotenuse. Segment is to altitude to segment. All those things true, correct? Specifically, what I want to use, though, is segment is to leg as to hypotenuse. I want to use it twice. So in letters, Audrey, how would I say segment is to leg is to hypotenuse? Good. AD is to AC as AC is to AB. That's one of the ways we could say segment is to leg is to hypotenuse. What's the other way, Kendall?
DB is to CD as DB, no.
Segment is to leg as leg
DB
is to
VA.
VA, the hypotenuse. There we go. It is because if altitude drawn to hypotenuse in right triangle, segment is to leg as leg is to hypotenuse. We'll just kind of roll with that. If altitude is drawn to the hypotenuse in a right triangle, then segment is to leg as leg is to hypotenuse. All right, now, look at what we're trying to prove. What is the prominent feature in what I'm trying to prove?
Squares.
The squares, right? Should be popping off the page to us now. Okay, how do I go about going from what I know to be true to ending up with some squares?
Rearrange it.
Square which now?
Can you rearrange it to make it look different? Or that probably doesn't help us, but
I want an AB squared, a BC squared, an AC squared. How do I go about getting squares from what I just wrote in number 3?
why don't you get not lowest common denominator, the square everything. Can't you just square the entire proportion?
I don't need to square the whole proportion. There's an easier way. Something we've been doing since we first saw proportions in Algebra 1. Cross multiply. Yeah. If I cross multiply right here, Quentin, what do I have? If it were to cross multiply right here, what would I get?
ABD.
Well,
Or A squared.
AD times AB, because again, this is all one quantity, and that's one quantity. So we'd say AD times AB equals AC times AC, which would be AC squared, right? On a similar note, what could I get if I took care of the other side there, Chris?
DB times BA equals CB squared.
I'm going to rearrange the letters, just put them alphabetically there. But yeah, BD times AB equals BC squared. And I guess I could use the parentheses here. I don't necessarily have to use the raised dot. So yeah, AD times AB equals AC squared. BD times AB equals BC squared. And we know that's true because in any proportion class, the product of the means equals the product of the extremes.
Can we use right principal theorem or whatever?
Do we ever do that? Fundamental property of proportions? No, only because that doesn't explain what it says, and it's frankly faster this way when you use shorthand. So product of means equals product of extremes will be how we can sort of abbreviate that fundamental property of
X
proportions.
equals product?
No. A multiplication symbol in parentheses means the word product.
Oh, I didn't know that.
Yeah, I taught that way back in the day.
I must not have been here for that.
Or you just weren't paying attention, which is much more likely.
Ow.
All right, so let's look at what I've got. Now, I don't have all my squares yet, do I, class?
Nope.
But I've got 2 of them are squared, right? The AC squared and the BC is squared. I just don't have the AB squared yet, but I got a little bit squared. What do I want to be true about these 2 squares that I have?
Equal.
I don't want to set them equal to each other. What do I want to do with them? I want to add them, right? So, what I want to do is I want to take this, and I want to take that, and I want to add them together, right? I want to take AC squared, I want to take BC squared, and I want to add them together. Well, you can add these 2 things if you also add their
Products. Their extremes are
equals, right? The extremes in this case, right? Add what they are equal to. So if I were to also take, and I'm going to run out of room doing it this way, but if I were to take the AD times AB, which of course is equal to AC squared. They're equal, right? We just said that in number 4. And I were to add these equal quantities, BD times AB, add that to one side, add the BC squared to the other side, then I'm simply adding equals to equals, right? That's called the addition axiom, right? If equals are added to equals, the sums are equal, and that's all we did here. You can add any 2 things together so long as you also add their equals together. That's what we did here. We took the AC squared and BC squared, added them, but we also added their equals to each other. Now, notice I'm pretty much set. All of this is now present. It's just this that I ain't got yet.
You get AD equal to
AB squared.
If you can get AD equal to BD.
Ooh, I definitely don't know that that's true. If the legs were equal, it would be true, but I don't know that's true. We're going to do a little bit of an algebra step here. Okay, so take you back to your algebra days.
Uh-oh.
I've got AD times AB plus BD times AB. Do you notice there's a common factor?
AB.
Yeah, AB. And we know that we can factor out common factors. So I can pull the AB out. It's going to leave me with a binomial AD plus BD. So that AB times AD plus BD equals AC squared plus BC squared. That's simply factoring. And that gets me one step closer to AB squared. How? Might help if you look at the picture.
AB equals BC plus AC.
The whole equals sum of its parts because AB is the whole hypotenuse.
Ah, so we know, because the whole is equal to the sum of its parts, that AB is equal to what, Chris?
The sum of its parts?
Which is?
AD and BD.
Yeah, AB equals AD plus BD, doesn't it?
Not equal to AC squared plus BC squared.
And so that's, you know, as Chris said, the whole equals the sum of all its parts. And so right here where it says AD plus BD, I could,
Where it says AD plus BD.
AB.
I could substitute an AB. So number 8, that means that AB times AB equals AC squared plus BC squared. But what is AB times AB? That's
AB squared.
AB squared. So we could also say then equals AB squared by a substitution.
So that's straight up.
And there we go.
Oh, this is going to be a lot longer than actual.
Nope.
Figured it's gonna
Again,
be-
really easy to prove once you know that segment is to legis, legis to hypotenuse. Some cross multiplication, an addition, a little bit of factoring, stating that the whole equals the sum of its parts, and there we go. Pythagorean theorem finally proven that yes, it is true. The square of the hypotenuse equals the sum of the squares of the legs. If you would, go and turn to the pictures and proportions part of your class notes. Pictures and proportions part of your class note. Now, I don't realize this is not actually a proportion, okay? But it's built off of the proportion idea, and it's a picture that we need to know really, really well. So in your pictures and proportions, go and draw a right triangle. Label the hypotenuse as small c. Label the legs as small a and small b. And simply write c squared equals a squared plus b squared. This is true of any right triangle. Nothing has to be special about it besides the fact that it's a right triangle. And once you got that in the pictures and proportions, go back to the theorems corollaries section. Theorems corollaries section of your notebooks. Corollary 62-1. Corollary 62-1. This is one of the more painfully duh corollaries, okay? Corollary 62-1 says this: in any right triangle, the square of one leg, in any right triangle, the square of one leg equals the difference of the square of the hypotenuse. In any right triangle, the square of one leg equals the difference of the square of the hypotenuse and the square of the other leg. In any right triangle, the square of one leg equals the difference of the square of the hypotenuse and the square of the other leg. It's essentially a two-step proof.
Is that the shortest proof we have?
Well, correction, it'd be a three-step proof. You'd have your given that you've got a right triangle. So number one, you're given right triangle, if we were to do the proof. Number two, as soon as you've got a right triangle, you know c squared equals a squared plus b squared. Of course, you'd use whatever lettering came with the triangle, but that's the gist of it. You quote theorem 62 as your reason. How would you prove that the square of one leg equals the difference of the square of the hypotenuse and the square of the other leg? Well, pick a leg, A or B. Audrey? A. So if I wanted to get a squared by itself, I'd have to subtract b squared from both sides, right? So that a squared equals c squared minus b squared. In other words, the square of one leg equals the difference of the square of the hypotenuse and the square of the other leg. Subtraction axiom. And we're done with the proof. Like really, really easy, right? It's just subtracting away one of the squared legs from the squared hypotenuse, leaving you with the square of the other leg. So we're not going to take time to actually do the formal proof, but obviously that's how it would work. All right. Notebooks aside, just have some paper out. Have your calculators out as well. Have your calculators out as well. Go ahead and draw on your paper a right triangle to the best of your ability. Go and label it right angle C, angles A and B. Right angle C, acute angles A and B. Now oftentimes, again, we will use lowercase letters here to show that this then would have to be side little a, because it's across from capital angle A. It's also called side BC. But we can call it side little a because we're lazy. We can call this side AB side little c because it's across from the right angle C. And we can call this side little b. It is side AC with the capital letters, but it's also side little b. Suppose I told you that A was 8 inches, B was 6 inches, and I wanted you to find the length of the hypotenuse. Well, very straightforward. You would plug this into the Pythagorean Theorem, which in short says, class, c squared equals a squared plus b squared. Again, what's the Pythagorean Theorem, class?
C squared equals a squared.
Okay, we kind of fell off the rails, so let's try to say it in unison here. C squared equals a squared plus b squared, where c is always going to be the hypotenuse, and a and b are the legs. So it's pretty easy. You might be able to do it in your head. We square the 8. We square the 6. We add the 64 and 36. And we take the square root because c squared is 100. C would be the square root of that, 10. Positive, negative? No, because we're dealing with a length just positive, 10 inches. Again, if you wanted to show out the steps, you could. C squared equals 8 squared plus 6 squared. I don't think it's necessary to show that. I think you can at least start with c squared equals 64 plus 36, which you could also say then just equals 100. The last step, of course, would be to take the square root. C equals 10. Questions on that? Let's suppose I knew that side A was 12 centimeters. I did not know side B, but I knew that side C was 13 centimeters. Well, in short, to solve this, we would need to set up the Pythagorean Theorem. And what is the Pythagorean Theorem, class?
C squared
equals a squared.
Oh, that was really bad as far as the unison. Let's try that again. C squared equals a squared plus b squared. But instead of c squared, we're going to plug in 13 squared, which is 169. How many remembered that without having to type it in? It's okay, you have a calculator if you didn't remember it. Equals a squared, but we're not going to write a squared. We're not even going to write 12 squared. We're going to write 144 plus, I don't know b, so we just have to write b squared. C squared, 13, equals a squared, 144 plus b squared. Now, to get the b by itself, I need to first subtract the 144 to get 25 equals b squared, so b is 5 centimeters. Make sense?
Yep.
Do we see how to solve either for the hypotenuse, square them, add them, take the square root, or for a leg, square them, subtract them, take the square root? What if you got a little mixed up and you added them? Do that on your calculator. 169 plus 144. What does that come to? 313. So that b is the square root of 313 centimeters. Now that doesn't come out evenly. In fact, I don't even know that that reduces.
17.691.
Comes out to approximately 17.69, you said?
Yes.
Is that possible that a leg could be bigger than the other sides?
No.
No. So you know something's wrong there. Oops, I added, I should have subtracted. By the way, we don't use decimals. We use radicals, either reduced or whole values. Okay, so in this case, we would have had to leave it as square root of 3, but it wasn't, right? We were finding a leg, so we have to remember subtracting the squares to get the leg. Let me have you do one of these on your own. Suppose I wanted to know side A. I knew side B was, let's just say 12 units, and side C was 37 units. At your seats, find the missing leg A. Gonna need the calculator here because we didn't memorize 37 squared. We didn't go that high.
Why would we?
No reason. What is 37 squared?
1,361.
1369. So there's your c squared equals a squared plus, of course we know b squared.
144.
Don't waste your time plugging that into the calculator. 2 more steps. First,
Minus 144.
subtract the 144 to get,
1,225.
but that's a squared. Again, you're not going to write, and I've seen students do this, and I'm like, does that not seem a little big to you? Okay, if your answer seems just absolutely ginormous, you probably forgot to take the square root.
35.
Now, this isn't one we memorized. Try it, and if it doesn't work out, we'll reduce it later. But always try it. And if you get a decimal, you hit the square button, just kick it right back to this number, and then we can worry about it later. But it does come out evenly, doesn't it, class? 35 units. Since no units given here, we don't need a unit given there. How many had the 35 units? All right, questions? All right, how about if I knew that side A was 21 units, side B was 20 units, and I wanted to find side C, the hypotenuse? Chris has it, Quentin has it. We're going to get our answer from Kendall.
29.
29 units is correct. Again, you get to the square root, I think it's 841. And you're like, I don't know what that is. Well, try it. If it doesn't come out evenly, we'll reduce it later. But try it just to see if it works out. And it did. How many have the 29 unit long hypotenuse? All right, any questions on that? All right, how about this? Let's suppose I told you that leg A was 10 units. We're looking for leg B, and leg C is 15 units. Leg A is 10 units. Leg B is, well, we're finding it, and leg C is 15 units. We're going to plug this into class the Pythagorean Theorem, which is?
C squared equals A squared plus B squared.
There we go. And again, I'm not going to write that out because I'm too lazy. I'm not even going to write 15 squared equals 10 squared plus b squared. I'm going to write out 225 equals 100 plus b squared.
Something ain't right with this one.
Subtract away the 100 to get
125.
125 equals b squared. Of course, we need to take the square root. Can we take the square root of 125?
Nope.
No. 121, yes, that's 11, right? So I know this is like 11.2, 11.3 maybe, something like that.
Yeah, 11.2 if you reduce.
11.2, okay. But I don't leave decimals. Since it doesn't work out evenly, I've got to reduce the radical. And generally, if we're looking over at the side bulletin board, we're going to do it the first way. That's the common way we're going to use in this class, is just factoring up our radicand. So 125, we need to find a square
25.
that's in 125. And Chris, you said?
25 to 5.
Right, this is 25 times 5. Now, class, can we take the square root of both of these?
So it'll be 5
No,
times
but we can take the square root of one of them. We can take the square root of
25.
25, which is
5 times
5. We're going to have to leave the square root of the 5 that was right here. So for our answer, not 11.2, but 5 times the square root of 5. Quick reminder, if you want to write these down on your paper, your squares are 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and so forth, right? Most of the time you'll use some of the earlier squares. But again, if you can get one of these as a factor, you'll be able to reduce down the radical. Questions on this? All right, how about this one? Let's suppose I wanted to find leg A. I knew that leg B was 5 feet, and I knew the hypotenuse was 15 feet. At your seats, find leg A. Again, start by thinking. Even if you don't write c squared equals a squared plus b squared, I usually won't. I'm lazy. If you were in 8th grade, yes, you'd be writing it. We're not in 8th grade. Okay, we just think c squared equals a squared plus b squared. We don't even write 15 squared and a squared plus 5 squared. We'll start by writing what, Genesis?
225 equals a squared plus 25.
And of course, we then need to
Bring the 25 as negative.
to get
200.
equals a squared. And can we take the square root of 200 evenly, Genesis? No, but we can factor it. 200 factors into,
100 times 2.
right, 100 times 2, where, of course, we can take the square root of
100.
to get
10.
times the square root of the
2.
2. And there's our answer. 10 times the square root of 2. Of course, we have feet here. We need to use feet in our answer. 10 times the square root of 2 feet. How many have that answer for side A? Okay, questions on this? Again, so if it doesn't work out evenly, that's okay. We got this. How about this? Supposing we knew side A was 6 inches. And supposing we knew side B was 12 inches. Find the hypotenuse. Side C. And Chris and Quentin finished first again. Ethan done as well. Do the guys have a clean sweep? Only if they all have the right answer. So let's attack the weakling first. Ethan, what? Why? Why? Can you tell I've missed you, Ethan?
Yes.
Ethan, what did you get for your answer?
3 squared root of 10.
It's not what I've got in my head, but I could be wrong. Did you get 3 squared root of 10? What did you get?
6 square root of 5.
That's what I had. Did you have 6 squared of 5? Yeah, so should have taken the c squared equals 36 plus 144, which would have given you 180. So c would be the square root of 180. Now, if you could do 9 times 20, which would be 3.
For some reason.
Oh, yeah, 10 times 9 would be 90. So 9 times 20, which is 4 times 5. So I would take the square root of 9 to get 3, square root of 4 to get 2. There's your 6 times the square root of 5 inches. All right, ladies, how many of you had 6 times the square root of 5 inches?
Wow.
I forgot the inches. All right, all right, minus a point. All right, questions on this? We good with Pythagorean Theorem? You get some practice with that tonight in your homework. For now, turn to page 212. Keep your paper out. We're going to keep working on some things. But page 212 in your textbooks.
Are we done with calculator?
Keep it out. And do a little bit more math. Going to use some problems that are in the book here. Page 212. Let's take a look at number 6. Number 6 on page 212. Now, we're referring to this picture. They're not using the 3 letters anymore. They're calling these sides AB the hypotenuse, BC the leg, AC the leg. All right, so this is the picture we're going off of here. Looking, if you flip the page back, Theorem 62. Okay, flip the page back, Theorem 62, that picture. They've got it laying on its side, but we can see that AC and BC are the legs, AB is the hypotenuse. All right, and it says that AB is to AC as 3 is to 2. And they tell us that BC is 35 inches. So on our picture here, you can do this with me on your paper, we know that BC is 35 inches. There's no mystery there. But AB and AC, it just says that they're in ratio 3 to 2. Thoughts?
Times 35 by 3, and then divide by 2.
We've seen this before. Maybe we've forgotten. After all, we did just have spring break.
That's it.
I've got 2 unknowns, right? I don't know AB. I don't know AC. But I know they're in ratio 3 to 2.
3 to 2 is 35 is to 1.
If I knew that Ethan's working now, he has money. Chris is working, Chris has money.
I don't know about all that, but
Let's say Jamie has money. All right? But Ethan and Chris, they're working. They got lots of money. So we'll say that Ethan to Chris to Jamie, the amount of money they have is in ratio of 9 to 8 to 2. 9x, 8x, 2x, right? Remember that now? Okay, so if AB is to AC is 3 is to 2, how would I represent AB and AC, class?
3x and 2x.
3x, 2x. Remember it now? So AB, 3x, AC, 2x. And it's a right triangle. And I'm trying to find sides of a right triangle, so I should use the Pythagorean Theorem, which is c squared equals a squared plus b squared. Now here, what is my c squared?
3x. 3x squared.
3x squared, in other words,
9x.
9x squared,
Yeah.
right? Okay, what is my a squared? Calculators.
1369.
1,225. What's my b squared?
4x squared.
4x squared. Do we see it? We're told that AB and AC are in ratio 3 to 2. Okay, call them 3x, 2x. Plug that right into the Pythagorean Theorem. No big deal here. But I've got an x squared on both sides, right? I can't have that. So we always get rid of the little one, remember? Sorry, Kendall. So, Kendall, which one's got to go? The 4x squared. I move it over as a negative 4x squared to get
5x
is equal to the 1,225. Now we've got this incomplete quadratic. We need to isolate the x squared by dividing both sides, class, by
5.
to get x squared equals
245.
who?
245.
245. Someone verify? I got it. Okay, 245. And then, but that's x squared. I just want x, right?
Square root.
Take the square root. I don't think that comes out evenly. It doesn't. But we can factor, right? X is the square root of 245. Is there a square in 245? 4, 9, 16, 25, 36, 49? Wait, 49.
Yeah.
49 times 5. Yeah, I was watching, I'm like, there's got to be one. Come on, there's got to be one of these. Yes, 49. 49 times 5. So my x comes out to
7 times the square root of 5.
7 times the square root of 5. But AB and AC weren't x. AB was 3x. So how big is AB?
21 times the square root of 15.
Ooh.
21 times the square root of 5.
21 times the square root of 5. Yeah, don't multiply a non-radical 3 by the radical 5. 21 times the square root of 5 inches. Someone besides Chris, what's the length of AC?
14 times the square root of 5.
14 times the square root of 5 inches. Questions on this? You're going to have a problem similar to
I don't like this.
questions on this. This is where we step it up just a little bit from out junior high math. Because frankly, most of what we did before this, you did in junior high. Not reducing radicals, but the rest of it we did in junior high. It's geometry now. It's 11th grade
not fun
or
anymore.
10th grade. So homework for this evening is to do page 212. Page 212, numbers 1 through 5. Page 212, numbers 1 through 5. We'll take a look at all of these tomorrow. Now, number 4, by the way, includes an altitude. So it's going to give you some practice with that. Segment is to altitude, is altitude to segment, segment is leg is to hypotenuse. The rest of them are Pythagorean theorem. Page 212, numbers 1 through 5, and you are dismissed.